Iron nitride permanent magnets, magnets without rare earth. In today's technological landscape, permanent magnets are the unsung heroes powering everything from electric vehicles and wind turbines to everyday electronic devices. For decades, the highest performing magnets, dominated by compounds like neodymium iron boron, NdFeB, have relied on rare earth elements, whose extraction raises both environmental and geopolitical concerns. Iron nitrides have emerged as a promising rare earth-free alternative, offering the potential to redefine the foundation of modern magnet technology. Iron nitrides, particularly in forms such as the alpha phase 6N2 phase, have attracted significant scientific attention due to their unique magnetic properties. This phase is reputed in some studies to exhibit an exceptionally high saturation magnetization owing to its unique crystal structure. Such a standing attribute is critical for the magnetic energy product, a measure of the magnet's strength and efficiency in energy conversion. If produced with a high degree of phase purity and optimal structural alignment, iron nitride magnets could, in theory, match or even approach the performance characteristics of traditional rare earth-based magnets. However, the reproducibility of these magnetic properties has been a subject of intense research and debate, highlighting the challenges that remain in consistently achieving the desired phase and microstructure. Creating high-quality iron nitride permanent magnets is not a trivial task. The synthesis process typically involves nitrogen incorporation into iron, which requires precise control of temperature, pressure, and chemical environment. Techniques such as reactive sputtering, plasma nitriding, and advanced sintering methods have been explored to achieve the metastable phases that confer high magnetization. The main challenge lies in stabilizing the alpha phase 6N2 phase, while avoiding unwanted impurities and competing magnetic phases. Researchers are continuously refining these techniques by experimenting with alloying additives and novel processing conditions that could promote phase stability while allowing for scale-up in industrial manufacturing. The high-performance magnets on today's market, such as those based on neodymium, owe much of their impressive magnetic characteristics to the inherent properties of rare earth elements. However, reliance on these materials comes with significant drawbacks. Rare earth magnets are expensive, their supply is often subject to geopolitical tensions, and the mining processes involved can have detrimental environmental impacts. Iron nitride magnets, in contrast, utilize iron, a plentiful and relatively inexpensive resource, combined with nitrogen. With further research and optimization, iron nitrides could potentially offer a pathway to producing competitive permanent magnets without the drawbacks associated with rare earth elements, thereby reducing both production costs and environmental burdens. The wide-ranging applications of permanent magnets mean that any breakthrough in material science could have cascading effects across several industries. Electric vehicles, renewable energy systems, robotics, and consumer electronics could all benefit from magnets that are both high-performing and sustainable. The adoption of iron nitride magnets, if industrially viable, would not only alleviate the pressures on rare earth supplies but also enable more predictable and environmentally responsible manufacturing processes. The shift towards such alternatives is a crucial step towards achieving a more sustainable, resource-efficient future in technology. Iron nitride permanent magnets represent more than just a novel material alternative. They embody the drive to innovate under constraints and to rethink the very components that underpin modern technology. Transitioning to rare earth-free systems is emblematic of a broader paradigm shift in how we approach material science in an era marked by environmental consciousness and economic pragmatism. While the journey from laboratory experiments to industrial-scale production is fraught with scientific and engineering challenges, the promise of high-performance, sustainable magnets is an inspiring testament to human ingenuity and perseverance. The exploration of iron nitrides is ongoing, and further advancements in understanding their intrinsic magnetic properties, enhancing synthesis techniques, and reducing manufacturing costs could one day make them a staple in applications where traditional rare earth magnets currently dominate.